Today we start our new unit, our second to last unit of the year, called Electromagnetic Radiation. You guys did a little bit of this, electromagnetic radiation, back, I believe it was grade 9 science. We talked about heat. Heat, thermal energy, is really just infrared radiation, a type of electromagnetic radiation. You would have learned the types of electromagnetic radiation back then, although you may forget. You would have learned exactly what electromagnetic radiation is back then, although you may forget. Electromagnetic radiation, we say, is EMR, or electromagnetic radiation, is energy that travels as a wave in a wave-like form without the need for a medium. And what do we mean by that? Well, a water wave, hey, we get a disturbance out in the middle of the ocean from a ship or from wind, and the water wave carries in towards the shore via a medium. The medium is the material, it's the water. You can't have that energy, bless you, go from the middle of the ocean to the shore without the medium. When I speak and you hear my voice, you can't hear the sound waves in your eardrum without the medium, without air. If there's no air in this room, besides the fact that we'd all be dead, okay, without air in this room, you wouldn't hear my voice because there wouldn't be a medium to carry the wave from my larynx to your ears. But electromagnetic radiation is a wave that can travel without the need for that medium, without the need for that air or that water. It's pure energy. It's pure energy that travels in a wave-like form as a transverse wave. You guys remember the difference between a transverse and a longitudinal wave? Transverse wave is this wave. Okay, longitudinal was that series of compressions and rarefactions. Okay, make sense? Remember that? So transverse wave without the need for a material. Now, that doesn't mean that it can't travel through a material. Visible light is electromagnetic radiation, and it's traveling through air right now. The light coming from that light bulb up there is traveling through the air to your eyes. The light coming from the sun, for the most part, travels through nothingness, the nothingness of space, but then when it reaches the Earth's atmosphere, it travels through the atmosphere and travels through the air coming down to reach our eyes. So it doesn't mean that it can't go through a medium, it just doesn't need that medium. Now, what exactly does it look like? Okay, we see visible light, but we can't see the wave nature of visible light. Well, just before you try copying this diagram, let me explain it, okay, because it looks a little bit confusing. Electromagnetic radiation consists actually of two waves. One of them is an electric field wave, and the other one is a magnetic field wave. And these two waves are not only perpendicular to each other, but they're in phase with each other. What do you think that means? Perpendicular means 90 degrees, right? What does in phase with each other mean? Yep?
They intersect at the same point.
Yeah, that's a good way to say it. They intersect at the same point. So basically, as you get a crest of one wave, you get the crest of the other. As you get a trough for one wave, you get a trough for the other. So it looks, I spent a lot of time, by the way, trying to draw this diagram. Okay? And in the end, I think it more or less worked out. You can see the vertical lines here representing my electric field, and then these horizontal lines representing my perpendicular magnetic field. If I was to do this, kind of show you the waves like this, okay, it would look something like this. Now, this is really hard to do, by the way, especially for men who have a tough time doing two things at once. Okay? We got one wave like this. We have another wave like this. So it kind of goes like this, in phase with each other. Now, I'm trying to do three things. I'm trying to talk. Notice I just stopped because I can't do that. Okay? So we got like this. It's hard. Try it if you don't believe me. Does it make sense what I'm doing here? We've got two sine waves. One is on one axis like this, say the z-axis, as I have it, and one is on the y-axis. Now, notice as well which way the wave is traveling. Okay, if we've got a wave, electric field on the y-axis and the magnetic field on the z-axis, which way is it traveling? On the x-axis. So we've got, it consists of a sinusoidal electric field wave, a sinusoidal magnetic field wave, perpendicular to each other, in phase with each other, and then of course they both travel perpendicular to both of those waves on the third axis, essentially. Does that make sense? Kinda? So, where does all this come from? Like, we've got this changing the sinusoidal electric field, sinusoidal magnetic field in phase with each other. Like, it's not just by chance. It's not just random that this stuff happens, right? When you flip on the light switch, it's not just a random generation of a wave that just happens to be by chance electric and magnetic fields sinusoidal perpendicular to each other. Where does it come from? Well, electromagnetic radiation was discovered by, or at least I shouldn't say it was discovered by, okay? Cavemen saw electromagnetic radiation, right? Because they looked up in the sky and saw the light coming from the sun. Okay, so electromagnetic radiation has been around literally forever. But in 1861, James Clerk Maxwell put forth a theory that described the nature of electromagnetic radiation, what it consists of, and where it comes from. He said in 1861 that accelerating charged particles generate magnetic fields. In fact, we knew this, right? We've learned this already. Charged particles that are moving, listen carefully, charged particles that are moving generate magnetic fields. Agree? We learned that in the last unit. You guys knew that, right? Charged particles that are moving generate magnetic fields. Charged particles that are accelerating generate changing magnetic fields. You got to think, if no movement causes no magnetic field, movement causes magnetic field, then change in movement causes changing magnetic fields. So accelerating charged particles, accelerating electrons, accelerating alpha particles, whatever, speeding up, slowing down, changing direction, accelerating charged particles generate changing magnetic fields. Now, changing magnetic fields will generate changing electric fields. Thomas used a word a minute ago, perpetuate. Electromagnetic radiation does perpetuate itself. Okay, we have a source, let's say over on the left side of the room over here, a source of EMR, whatever it is, some accelerating charged particle generates EMR. The EMR doesn't stay there at that place, it perpetuates itself and moves to another place. Here's the accelerating charged particle that generates this, we'll make the magnetic field on the y-axis this time, okay, that generates this changing magnetic field. And at the same time, it generates this changing electric field. So we've got a changing magnetic field and a changing electric field. Now, the charged particle isn't accelerating more. It's done. Okay, it's done its thing. This changing magnetic field and this changing electric field will generate this magnetic field and this electric field, which will generate this magnetic field and this electric field, which will generate this magnetic field and this electric field. Does that make sense? Now, let's say that accelerating charge just generated the one pulse. We're not saying that now all of a sudden we have this big continuous wave like this. This crest of a magnetic field gets replaced by this trough of an electric. And this crest of an electric gets replaced by this trough of a magnetic. And then the magnetic trough gets replaced by an electric crest. And the electric trough gets replaced by a magnetic crest. And so on and so on and so on. Right? Does this all make sense? Okay? Like perfect sense? Okay, so probably look up here, right? So accelerating charged particles generate this and this. And then this and this generate that and that, which generate this and this, which generate that and that, and so on. So now we've got the original production of the changing electric field and magnetic field, that one basic pulse, but it moves or it propagates perpendicular to both of those waves because of changing magnetic fields generating changing electric fields and changing electric fields generating changing magnetic fields. So there we got not only the composition of the wave, but the propagation or the movement of the wave as well. So to summarize, EMR consists of changing electric and magnetic fields, or sinusoidal. Just means sine waves, right? Perpendicular to each other, perpendicular to the way that it moves, and in phase with each other. And they're generated It's generated by accelerating charged particles. Now, we're going to spend this unit, it's a fairly long unit, we're going to spend this unit talking about EMR light, visible light, all these other kinds of EMR, is either a wave and or a particle. And depending upon the context in which we're talking, we may describe it as either or both. For now, we're going to describe it as a wave. Now, prior to Maxwell, there was a lot of debate as to whether light, particularly visible light, but EMR in general, is a wave or a particle. But when Maxwell came along in 1861, like the debate was settled. Like it's a wave, right? Maxwell's got this great theory that describes it really, really well. It makes sense. It's perfect. Light is a wave. The debate that had gone on for centuries was over for a few years. It was a wave. We now know that it actually has properties of both waves and particles. But for the first part of this unit, we're going to focus on the wave nature of it. The wave nature of EMR is supported by 4 different properties of these waves, or 4 different properties of waves in general. Waves will diffract. Do you guys remember from Physics 20 what diffraction means? Anybody? Yes?
The angle the wave enters in the medium can change?
No, you're thinking of refraction. You're thinking of refraction. Diffraction is the spreading out of a wave. So if a wave is encountering an opening like this, then the wave goes through and spreads out like this. Spreads out through an opening or spreads out around a barrier. That's diffraction. And that's a property of waves. Only waves will diffract. But EMR diffracts, so EMR must be a wave. You guys remember what interference is? If you have a wave like this, and you have another wave like this, then it produces a bigger wave like this, constructive interference, right? 2 waves make a bigger wave, or 2 waves can make a smaller wave as well if it's destructive interference, right? But certainly that's a property of waves. Interference is definitely a property of waves, but guess what? EMR exhibits interference, so it must be a wave. Refraction is the bending of a wave or the changing of direction of a wave as it encounters a new medium. And I think that's what you were talking about a minute ago there, Thomas. As we have, let's say, a boundary between 2 materials, let's say the wave is traveling this way, gets to the boundary, and now the wave travels this way. That's a property of waves. Waves refract or change direction when they go into a new medium. But guess what? So does EMR. So if a wave property is exhibited by EMR, then EMR must be a wave. And finally, polarization is a property of waves. Polarization is like a filtering out of components of a wave. The analogy would be if I have a piece of plywood right here, and I have a groove in that plywood cut horizontally like this, and I have a rope going through that opening in the plywood. And the 2 people at either end of the rope are flicking the rope back and forth like this, producing a wave. You know what I mean? Okay, you're producing a wave like this. If they flick it this way, then they produce a horizontal wave. If they flick it this way, then they produce a vertical wave. If that wave is going through this opening and it's horizontal, the entire wave will make it through. If I flick it vertical, then none of the wave will make it through because the slit or the opening is cut horizontal. We would say that wave is polarized horizontally. Does that make sense? When you filter out components of a wave and only allow certain components to go through. That's a property of waves. but it's a property that's exhibited by EMR, so EMR must be a wave. All right, what are our types of EMR now? We know what it is. We know that we have different types of EMR. What are those types of EMR? Understand when I give you these types of EMR, understand that they're really just variations of the same thing. We have visible light. Visible light in the middle. Visible light is fundamentally not much different than X-rays or than gamma rays. The only difference really between visible light and X-rays or gamma rays is the frequency, and therefore the energy and the wavelength of these. You guys remember what the order of them would be from that movie, from that song that we played for you before? Radio waves, yeah. Next one is? Okay. Radio waves, microwaves. What's the next one? Somebody over here. Infrared radiation, we'll call it IR. Visible light, ultraviolet, X-rays, and gamma rays. Good. So we would say that radio waves have the lowest frequency, gamma rays have the highest frequency, and there is a tremendous range here. Okay, a big, big, big range. I'll give you those ranges in a minute here. Radio waves would also have the lowest energy. Gamma rays would have the highest energy. X-rays and gamma rays have the ability to penetrate matter way more than radio waves do, and that's because they have such a high energy. That's why we use gamma rays for cancer treatment. That's why we use X-rays to see inside our bodies, to see the broken bones. Radio waves, low frequency, low energy, but high wavelength. Because if you remember from Physics 20, frequency and wavelength are inversely related to each other. If we have a low frequency, then we have a high wavelength and vice versa. So whenever we're ranking these, like we did in the song, radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, gamma rays, we're ranking them from lowest frequency to highest frequency, or from lowest energy to highest energy, or from highest wavelength to lowest wavelength. We know that each one of these types of EMR, electromagnetic radiation, are produced by accelerating charges, but specifically, there's specific mechanisms that produce the different types. We're going to group radio waves and microwaves together. We're going to say that they're produced by oscillating electric charge. What does that mean? Oscillating. We know what electric charge is, right? What does oscillating mean? Back and forth, back and forth, back and forth. So radio waves, listen, there's a band of radio waves just like there's a band of visible light. But we're making it one big category right here, one big category of microwaves, which are often used in a similar way to radio waves, right, for communication, but also for cooking your food in a microwave oven. They're produced by oscillating electric charge. Electric charge is going back and forth, back and forth, back and forth. Infrared, visible light, and ultraviolet are all produced in a similar way as well. They're all produced by transitions of electrons in atoms from high to low. So in other words, if an electron makes a transition from level 3 down to level 2, some form of EMR is given off, infrared, visible light, ultraviolet. Occasionally an X-ray can be given off that way as well, but it would have to be a really, really big transition. So usually we just say these three types, infrared, visible light, and ultraviolet, are produced by transitions of electrons in atoms from high to low levels. Now, it's not just random which one is produced. each transition is associated with a specific type of EMR. The bigger the transition, the higher the frequency, the higher the energy of the EMR that's given off. So if you have a really small transition, let's say from level 2 to level 1, it's going to be infrared given off. Smallest transition is going to be infrared given off. If you have a really big transition from, let's say, level 6 to level 1, then you're looking at probably ultraviolet given off. X-rays, the X-rays that are used at the dentist office or at an imaging clinic or that are used at the airport for finding hidden stuff, are produced by rapid deceleration of electrons. So these electrons are going really, really, really fast, like 10 to the 7 meters per second fast, and then they're smashed into a target, and they stop almost instantly. They had all this kinetic energy that's got to go somewhere, and this kinetic energy gets transformed into light energy. Not light that we can see, right? It gets transformed into X-ray energy. We said a minute ago, what's the difference really between X-rays and visible light? Nothing really, except the frequency, and therefore the wavelength and the energy. We use X-rays to see all the time, right? We use infrared. You saw in the video, infrared is used to see, right? We pick up, if we can detect, infrared is heat, right? Thermal energy, heat. If we detect the heat signature of somebody in the dark, then a computer can plot a picture of that, and we can see the image. Okay? Same thing with X-rays. X-rays have a much higher penetrating power than visible light. Okay, when I shine visible light on you, I can see the outside of you. Why? Because the outside of you reflects visible light. But if I shine X-rays on you, well, I can't see X-rays, but let's pretend I could for a second. Certain cameras can see X-rays. Okay? If I shine X-rays on you, well, then I don't see the outside of your body. Why? Because X-rays don't reflect off of the outside of your body. What do I see? I see your bones, because X-rays reflect off of your bones. They have a higher ability to penetrate matter. They don't penetrate the bones. They reflect off of the bones, but they penetrate your skin and your tissue going into the bones. Make sense? Gamma rays are produced by nuclear decay. And what I mean by that, nuclear decay, is matter, like mass, literally being converted to energy. Now I got some good news and bad news for you. Where are you going first? Bad news? Okay. There are 7 different types of electromagnetic radiation. The lines between them can actually be a little bit blurry in terms of which one is which. Like sometimes we may classify a certain EM wave as a radio wave. Sometimes we may classify it as a microwave. The lines are not hard and fast. Okay, but by and large, there are these categories with fairly specific frequencies, fairly specific wavelengths, and fairly specific energies. We have to be able to identify any EM wave, given its frequency, given its wavelength, given its energy. We have to be able to identify it as a radio wave, visible light, ultraviolet, gamma ray, or whatever. So that means you need to be able to identify 7 different ranges of frequencies, 7 different ranges of wavelengths, and 7 different ranges of energy. So 21 different ranges of numbers with exponents that we have to be able to identify. Okay, that's the bad news. The good news is, I'm only going to ask you to remember 3. Remember 3 ranges. There is no way around this. Okay, you have to memorize these 3 ranges. Got it? No way around that. But because with the little system that I use for this, If you remember these 3 ranges, then that will save you from trying to memorize the other 18 ranges. So invest a little bit of time, memorize those 3 ranges. We're going to say for frequency that microwaves have a frequency range of 10 to the 9 to 10 to the 12 hertz. Visible light has a frequency range. We're a little bit more specific with visible light. A, because that's what we can see, and B, because the range is so much narrower for visible light. We're going to say 4 times 10 to the 14 to 7.5 times 10 to the 14 hertz. So all within that narrow range of 4 to 7.5 times 10 to the 14 hertz. And X-rays, we're going to say are 10 to the 17 to 10 to the 19 hertz. Now, if you get a question where you're told that here's an EM wave and it has a frequency of 10 to the 11 hertz, we know right away, if we memorize these 3 ranges, that it's microwaves, right? If it's 5.5 times 10 to the 14 hertz, we know right away it's visible light. If it's 10 to the 18 hertz, we know right away it's X-rays, right? If we have these 3 ranges memorized. But what if it's 10 to the 6? We don't have that one memorized. What's it got to be? Radio waves, right? We don't have to memorize the range for radio waves, because if it's not microwaves, it's got to be radio waves. What if we get one that's 10 to the 15 hertz? We don't have that memorized. But how do we know it's ultraviolet? Because it's in between visible light and X-rays. Don't memorize a range for all 7 of these things. Memorize these 3, and then just figure out the rest of them for frequency. Make sense? What if you got 3 times 10 to the 14? What would that be? Infrared. Yeah, we'd still say it's infrared, even though it's really, really close to visible light. 10 to the 19, if I had 10 to the 21, we'd say that would be gamma rays, right? Because it's above 10 to the 19. Make sense? Now, what about wavelengths? What if I was given a wavelength of, I don't know, let's say 5 times 10 to the negative 7. 5 times 10 to the negative 7 is my wavelength. What type of EMR is that? Well, I don't know. That's not, I didn't memorize wavelengths. I memorized frequency. Well, what I want you to do, if you're given a wavelength, is to calculate the frequency. You can do that by saying frequency is V over lambda. What's V? Speed of light. For all 7 of these types, V, in a vacuum that is 3.00 times 10 to the 8 meters per second. So in the example that I just gave you, we would say frequency would be equal to 3 times 10 to the 8, divided by 5 times 10 to the negative 7. We would calculate that number. Listen, I don't really want to do a calculation here, but it beats memorizing 21 different number ranges, right? I get 6 times 10 to the 14 hertz. What type of EMR is that? Visible light. So we remember 3 different ranges of frequencies. Memorize them. No way around it. We've got to memorize these 3 ranges. And if you've got a frequency, either match it up with the 3 ranges that you've memorized or fill in the blanks. If you're given a wavelength, then get the frequency and match it up with the frequencies that you've memorized or fill in the blanks. If you're given an energy, you're going to do a similar thing. I'm just not going to give you what that equation is yet. That's going to come later on in this unit. But just understand that you can do the same thing with energy. It's just a different equation, not F is equal to V over lambda, that's all. So there's our types, there's how they're produced, there's the frequencies and so on. Last thing we're going to do today is how we verified Maxwell's theory. Like what experiment showed that Maxwell's theory was correct, more or less at least correct. Well, Hertz induced a big potential difference. He caused a really, really big potential difference across a gap. He called it a spark gap. Cause the electrons to accelerate across this gap. The picture looks like this, but the details of this aren't all that important, to be honest. This is called a transformer. The purpose of the transformer is to cause a potential difference to get bigger. Okay? The mechanics of that aren't important. Bottom line is over here, okay, this is the real important part over here. Over here, we've got a big potential difference. And that causes electrons to jump across that gap. Even though there's no wire there, they'll arc across that gap. And as they do that, they accelerate. And as they accelerate across that gap, if Maxwell's right in his theory, then they'll generate EMR. So Hertz introduced an antenna here, which is just a loop of wire, to detect that EMR. If EMR is, as Maxwell says, consisting of changing magnetic and changing electric fields, then that changing magnetic field in the EMR should generate an electric current in that wire, in that antenna. That's how antennas work. Did you know that? Like your radio waves strike the antenna on your car, it generates an electric current in that antenna, and then it goes to your radio and so on. So, Hertz fires this thing up. Electrons jump across the gap. They accelerate across this gap. And guess what? He detects a current in the antenna. So in other words, he says, oh, look, EMR must be present. And it must be caused by the accelerating charge. And it must consist of a changing electric and magnetic field. All that stuff must be the case. Otherwise, I wouldn't have detected it. If it wasn't consisting of electric and magnetic fields changing like Maxwell said, he wouldn't have detected a current in the antenna. If it wasn't produced by accelerating charges, then he wouldn't have ever had a current in the antenna because there would have been no EMR produced there. So, simple little experiment, detects electric current in the loop of wire of the antenna, which essentially supported all of Maxwell's theory that A, accelerating charged particles generate it, and B, it consists of a changing electric and magnetic field. The type of EMR that he detected, by the way, were radio waves. And the reason he used radio waves is because they're the easiest to make. Just involve charged particles accelerating back and forth. A little bit of homework. You can work on it for the rest of class here. Page 647. Good news is it's not all the questions. We got 1, 2, 5, and 7 to 14. 1, 2, 5, and 7 to 14, please.